Okay, in this example, we're going to take a look at a throw-up problem where delta y is equal to 0. Now, the facts of the problem are this. Two boys are throwing a ball, and the baseball follows a parabolic path that returns where the baseball returns to the same height. We desire to know what is the initial velocity of the baseball, knowing that the angle is 15 degrees. We also know that the range for the baseball, dx, is equal to 45 meters. So in order to calculate this, we're first going to label or identify our information for the x dimension and the y dimension separately. So in the x dimension, we have dx is equal to 45 meters. Vx is unknown. And t is also an unknown quantity, but it is something that we're going to be looking for. In the y dimension, we know that delta y, which is the same thing as dy, is equal to 0. We know that the ball has an initial velocity in the y dimension, but we don't know what it is. We know that the final velocity in the y dimension is equal to the initial velocity in the y dimension, but it's the opposite direction, so it's minus v initial y. We know the acceleration is equal to minus 9.8 meters per second squared, and that's because we're saying down is the negative direction, and time, of course, is something that we're looking for. Okay, so the first thing we're going to do is select the equations which we think are going to make this problem easiest to solve. In the x dimension, that's easy. It's always going to be dx is equal to vx times t. Now the y dimension, we've got three equations that we can choose from. So which one should we actually use? Well, let's take a look at what we've got. So looking at these equations, we've got v final squared equals v initial squared plus 2ad. Seems like a nice choice because we don't know what time is. However, the problem with this is that the displacement is 0, and we end up with v final equals v initial, and that's not very helpful. If we look at the acceleration independent equation, first of all, we do know what the acceleration is, so there's no reason to exclude it from what we're doing. D is equal to 0, and by the time you move 1/2 in t to the other side, we come back to this statement that v final is equal to a minus v initial, and that's not very helpful either. We already know that. And then finally, we've got d is equal to v initial t plus 1/2 at squared. That could be a valid option, but we need to be careful because this equation is quadratic, and we may end up having to use a quadratic formula if we're not careful. Remember, we're trying to eliminate time from our equation as much as possible because we don't know it. Now, other options could be, looking at our definitions, we could redefine time by saying it's v final minus v initial divided by a. So we can use this equation to redefine things. So why don't we try that? In the y dimension, we're going to say that v final y is equal to v initial y plus at. And now we've got to pick one of these equations as our primary. It doesn't really matter which one you pick, but sometimes it's a little easier to pick one over another. So in this case, why don't we stick with dx is equal to vxt? And we'll start by working with this equation first. So let's go through our checklist of variables and see, do we know dx? Well, we sure do. It's 45 meters, so let's put a check there. Vx, we don't know that. Time, we don't know that. So, we need to redefine things. What we do know is that Vx is going to be equal to V initial cosine of theta. So we'll redefine that as V initial cosine of theta times t. Going through our checklist, dx, got it. V initial, that's what we're looking for, so we don't want to eliminate it. Theta, we've got it. Time, we still don't know. So what do? We don't really have any other options for the x dimension because there's no acceleration. So for that, we go to the other dimension. And in the other dimension, what we're attempting to do is eliminate time here. So we have to solve this equation for t so that we can eliminate t on the other side. So we get v final minus v initial divided by a is equal to t. So let's put that into our other equation. And we get dx is equal to v initial cosine of theta times the quantity v final minus v initial divided by a. Okay, so this is all for the y dimension. We know that v final is equal to a minus v initial, so we get dx is equal to v initial cosine of theta times a minus v initial y minus v initial y over a. So dx is equal to v initial cosine of theta times 2 v initial sine theta. And this is all divided by a. So simplifying this a little further, we get, forgot my 2. We get a minus 2 v initial squared cosine theta sine theta divided by a. All right, now all we have to do is solve this for v initial. So to get v initial, let's rewrite our equation. Dx is equal to minus 2 v initial squared cosine theta sine theta divided by g. And then solving for v initial, we get g times dx divided by minus 2 cosine theta sine theta. And we'll take the square root of all of that to get v initial. Substituting values, we get the square root of minus 9.8. We have not taken care of that negative sign yet. Times 45 divided by a minus 2. And now we get the negatives cancel out, which is good because we can't take the square root of a negative number, times the cosine of 15 degrees times the sine of 15 degrees. Now let's calculate this. So we're going to get the square root of 9.8 times 45 divided by the quantity of 2 cosine 15 times sine 15. And the initial velocity is 29.7 meters per second. So that's a really fast ball. That's like a 100-mile-an-hour fastball. So I'd say these aren't boys throwing that ball. Okay, now we want to know what the time of flight is. To determine the time of flight, it is not necessary to follow the whole path. We can look at just the vertical motion or the horizontal motion. So you have a couple of choices. If we try to stick with only the information we're given, I don't know if that's possible. So we're just going to use derived information. And for that, we could just say dx is equal to vx times t. And that means t is equal to dx over vx, which is 45 over 29.7 cosine of 15. So we get our calculator out. 45 divided by 29.7 times the cosine of 15 degrees, and we get 1.56 seconds.